Today, we take a step back from G.E. Moore to look at the work of Frege because, as we've talked about, Moore's primary contribution, besides the substance of his own work, was to convert Russell to a realist stance as opposed to his earlier idealist stance, and also to influence methodologically the direction that the history of analytic philosophy took. In order to understand that direction, we looked at the refutation of idealism. And here's the crucial thing that I want you to recall from that paper. The central idea in the paper is that when we represent the relationship between a property and an object, say my car is black, we should represent that differently than we represent a relationship between a mental state and its object. Even though in both cases we have some object and we have something else, we should represent the top one in one way and the bottom one in another way. So, in the case of, say, the sensation of blue or the experience of blue, let E be the operator. I'm having an experience. There is an experience by me of something. Maybe the experience is the blueness of the sky. The blueness of the sky is just BS. I hope you like my symbols. Maybe they'll brighten your day. In any case, the relationship between a property and an object and a relationship between a mental state and its object need to be represented differently. Why is that important? The reason it's important is because for G.E. Moore and the origins of analytic philosophy, we are trying to understand something about the ultimate nature of reality. And in particular, at the beginning, the question is what to make of idealism. Is idealism true or false? And what Moore is slouching toward is the idea that we can make progress on the question of the ultimate nature of reality by paying attention to language and how it works. So sometimes the history of analytic philosophy is described in terms of making the linguistic turn. Instead of focusing on other issues, we're going to make language itself and its encoding in the mind the primary focus of how to make progress, how to try to generate understanding in philosophy. This phrase, the linguistic turn, by the way, is due to Richard Rorty in a volume he edited in the 70s called The Linguistic Turn. In any case, the idea is this. We have language over here, and we have reality over here. And these may be overlapping circles, but they're certainly not identical circles. So how do we link up our understanding of reality with our understanding of language? Moore's contribution in the refutation of idealism is that this overlap area helps us make some progress metaphysically through the notion of logical form. If we want to understand the nature of consciousness, the nature of mental states, the nature of reality that's apart from mentation, what we do is we look at how we should formulate, how we should structure an understanding of our language about such things. Once we do that, we're in a position to say consciousness is a distinctive kind of thing. It's not to be modeled on the same sort of logical representation as we got when we were talking about properties and their objects. It's just a different kind of thing. The object in question is not the same kind of object, although it can be. The object could be a proposition rather than a thing in the world. And the mental state in question is not to be looked at as a property of that object, but rather as an operator on it. So we have the sentence, for example, 2 plus 2 equals 4, which is true. And then we have various beliefs that can hold or not hold with respect to that claim. So maybe there are people who believe that 2 plus 2 isn't 4, but most of us believe that it is. This operator is an operator on this sentence. It is not a property of the sentence. Perhaps there's some way of talking about the sentence having a particular property, but the right way to understand the logical form of the sentence, I believe that 2 plus 2 equals 4, is there is an operator, I believe. It has an object or a content, 2 plus 2 equals 4, and the entire thing is to be represented this way. Then we will give semantic clauses for how to calculate a truth value for each of the kinds of sentences we have in our logic. Once you start thinking that way, which was how Russell was thinking, Russell was a much more formal kind of person working in the foundations of mathematics than was Moore. But Russell was impressed with this way of thinking about the connection between metaphysics, between reality and language, that the key to understanding the nature of the world was in our formal representation, in our logic. Logical form provides the bridge between language and logic on the one hand and reality on the other. Jump back then to Frege in the earlier, about 25 years earlier than when Russell and Moore first started showing up on the scene in the early 1900s. Frege too was working in the foundations of mathematics. What's important to realize about this part of the 19th century is there came to be a predominant preoccupation with the notion of precision in language and thought that spanned a whole bunch of different disciplines at the time. The cause of this focus on precision was the slowing down of successes in science, especially those derived from Newtonian mechanics. The story of Newtonian mechanics is, first, you get Newton developing the 4 laws of motion, and then over the next few centuries, you get success after success after success in applying this structure to outstanding problems in the history of science. By the time you get to the middle 1800s, Newtonian mechanics isn't having the success rate that it had previously. So people started wondering, what's going on here? Why are we not being as successful as we used to be in developing new scientific understandings? And the common response was, we're not being careful enough. We're being sloppy in our formalizations, and so our testing procedures turn out to be murky at best. We do an experiment, but it's not obvious what it refutes, what it confirms, because the setup is sloppy. So we need much more precision. So you see this in physics, you see it, as we will see, in philosophy, but you also see it in the sciences more generally and in mathematics. Frege is a key figure in the history of mathematics. Frege thought mathematics had an advantage over other disciplines, even though it's related to the sciences. The cool thing about mathematics is it's not corrupted by empirical contingent matters. It is pristine, and yet Frege complained that when mathematicians in the middle part of the 19th century sent proofs to each other and said, look what I've discovered, there wasn't any obvious way, apart from having a moment of insight, to tell that what they had done was prove something. They sent proofs that were not as precise as Frege thought they needed to be. Frege's solution to this problem was we need a firmer, better grounded foundation for mathematics. And his approach to this was what we need to do is ground all of mathematical reasoning in logic. Logic will provide the appropriate way of understanding what's going on in mathematics when it's applied to whatever whatever structure the mathematician is thinking about. The problem is the state of logic at the time of Frege was not exactly unified, complete, or well understood. The logic at the time of Frege was just the logic of categoricals that was inherited from Aristotle. So Aristotle intended to develop a logic that was adequate for use in science, and he did that in terms of 4 propositions. They are typically referred to as A, E, I, and O for all S are P, no S are P, some S are P, and some S are not P. That's what A is about here. They're called A, E, I, and O because 2 of these propositions are affirmative propositions and 2 of them are negative. The Latin words for affirmative and negative are affirmo and nego. And so they took the first vowels in each of those. And so you get A and I as the 2 positive propositions, because affirmo is A and I as the first 2 letters. Nego, E and O, for the negatives, no S or P, and some S or not P. The claim Aristotle was making was that we could understand the reasoning we engage in science by the use of these 4 kinds of propositions and the relationships between them. The one relationship that withstands scrutiny here is that A and O are contradictories, as are E and I. The negation of all S or P is some S or not P. The negation of no S or P is some S R P. Other relationships were introduced, but they don't withstand scrutiny. For example, A and E are said to be contraries. They can't both be true. I and O are said to be subcontraries. They can't both be false. The problem with introducing these additional relationships, purportedly logical relationships on the 4 kinds of propositions, is it allows an inference from all S or P to some S or P, which is called subalternation. Subalternation commits the existential fallacy. So it's true that all unicorns are things with a horn in the middle of their head, but it's not true that some unicorns have a horn in the middle of their head, because there aren't any unicorns. That's the existential fallacy. So once you purge the logic of categoricals of this fallacy, all you're left with are the contradictory relationships between A and O and E and I. They have to have opposite truth values. The other thing to notice is that all 4 of these propositions are general propositions. So think of the claim, Joe Biden is the President of the United States. That's not a general proposition, that's a particular one. So how are you supposed to express Joe Biden is the President of the United States in the logic of categoricals? Well, you have to do some fancy maneuvering to generate a general proposition. So for example, perhaps you can say all persons identical with Joe Biden are persons who are the President of the United States. There are ways to try to do this, but the general power of the logic of categoricals is limited in a number of ways. First, not all propositions are general ones, so you have to do some fancy footwork to do that. And second, the logic of categoricals didn't have any semantic device attached to it, where you can characterize a valid argument in terms of the impossibility of the premises being true while the conclusion is false. For that, you need some semantic apparatus to link each of these kinds of sentences with truth values. That's what semantics does. It gives you some sense of meaning. Other than that, you have no notion, other than a purely syntactic one, about what argument forms are valid and what aren't. So the study of logic in the Middle Ages turned out to be the study of which forms of syllogism were valid and which aren't. So syllogisms are forms of argument that have three claims. And each of the claims, two of those claims will be premises involving A, E, I, or O propositions. And the conclusion will also be a sentence of that form. Now, when you do a syllogism, you'll have one of the premises having the subject term in it, one of the premises having the predicate term in it, where the conclusion links those two, S and P, either in terms of all know, some are, or some aren't. So you look at that, and then each of the premises, of course, has to have another term, and that term will be shared in common. Call that the middle term. So a syllogism is a set of three claims, two of which involve the middle term, and the conclusion of which links the other two terms. Now, some of these arguments of this form are valid and some aren't. So what we need is a way, and this is what the study of logic gave us, we need a way of characterizing all possible combinations of these three kinds of things. So notice for the premises, you can have the middle term come first when linked to the subject term, or second. So you could have all M are S or all S are M. So you have four kinds of propositions linking S and M, and you have two possible places for the M term to appear in one of the premises, and the same for the second. So you can develop four possible combinations of where the middle term appears. But the point is, you can characterize every possible argument in terms of the form that the middle term takes, 1, 2, 3, or 4, and the combination of kinds of sentences that we have. Now, what you'd like is some general way of understanding which combinations of mood and figure give us valid arguments and which don't. A good semantics would do that. Unfortunately, there isn't one. There isn't one until, I believe it's 1892, when Venn diagrams first show up in the history of philosophy. Venn was a mathematician. Venn diagrams allow you to fill in various parts of that diagram. A circle for the S class, a circle for the P class, and a circle for the M class. So if you've got all S or M, what that tells you is everything inside the S circle that's outside the M circle is empty. And then you've got, as a second premise, all M are P. That tells you everything in the M circle outside the P circle is empty. And then the conclusion says all S are P. So then you inspect the diagram to see, is there anything in the S circle that's outside the P circle? Well, that's this part. The S circle that's outside the P circle, as we can see, all gets crossed out. The only remaining part of the S circle is right here in the heart of the diagram, and it's empty. It's not marked out. I'm sorry, it's not empty. It's non-empty. What's crucial is that the conclusion says all of this area is empty. And that's what our diagram of the premises does. But when you're talking about Frege working in the 1870s initially on the foundations of mathematics, there is no such device. And in the Middle Ages, when people would study logic, they would simply memorize the list of things that were thought to be valid syllogisms. They did so in the form of songs. They would invent songs that were mnemonic devices to help them remember. And they used women's names. For example, if your song had the woman's name Barbara first in the song, then that told you AAA in the first figure is a valid argument. So you'd sing a song and you'd have Barbara as the first name mentioned, and that would remind you AAA in the first figure is a valid argument. This is not the best way to think about logic. I mean, don't we want something better than this? Frege thought yes. So Frege was worried about the proof theory for mathematics and the kinds of proofs that mathematicians were sending to each other. And the only way to tell that the thing was a proof was to have this moment of insight. And Frege thought that's a crappy way to tell whether you've got a proof or not. This is supposed to be completely mundane. The hard work is figuring out the proof, but detecting whether something is a proof once it's put in your hands is not supposed to be complicated or difficult or require insight. This turns out to be the fundamental assumption underlying computer technology. Think of how computers work. At bottom, there are just on-off switches for electrical circuits. To get the program to run, you just have to sequence the thing properly. The computer doesn't need to understand any of the inputs or anything else. It's just a matter of the architecture doing what it's supposed to do. Frege thought that's what logic should be like. So Frege invents a powerful new logic. He generates this logic from his understanding of the notion of a function in mathematics. And that's what the paper Function and Concept is about. So Frege's new beginning says sentences and assertions bear a certain important relationship to the mathematical notion of a function. Now, Frege did something that is not right. So he tried to encode the force of a sentence, of an assertion in particular, in the symbols that were being used. We're going to bypass that issue, but Frege wanted, if we used symbol P for a sentence, he wanted to say, when we're doing logic, we're talking about assertions. And he put this assertion stroke in front to represent that. It turns out there's nothing you can do to encode force into the symbolism. That's something that's outside the syntax of the language. So let's skip that part for now and look instead at what he's doing. I'll read you the quote, the judgment stroke. It's important to notice that this is a mistake, but here's Frege. If we write down an equation or inequality, for example, 5 is greater than 4, we ordinarily wish at the same time to express a judgment. In our example, we want to assert that 5 is greater than 4. According to the view I am here presenting, the sentence 5 is greater than 4 and 1 plus 3 equals 5 just give us expressions for truth values without making any assertion. This separation of the act from the subject matter of judgment seems to be indispensable, for otherwise we could not express a mere supposition, the putting of a case without a simultaneous judgment as to its arising or not. So here Frege is right. Judgments and suppositions are different things. We thus need a special sign in order to be able to assert something. To this end, I make use of a vertical stroke at the left end of a horizontal, so that e.g. by writing assertion stroke 2 plus 3 equals 5, we assert that 2 plus 2 equals 5. Thus, we are not just writing down a truth value as in 2 plus 3 equals 5, but also at the same time saying that it is true. Now here we get some of the idiosyncratic features of Frege's semantics. He thinks that refers to a truth value. And he thinks to say that that claim is true requires something else. We don't need to go down that path. What we want to do is try to figure out what Frege is up to in terms of formal systems and methods first. So let's back up, forget about his distinction between sentences and judgments. Instead, look at the history of mathematics about the relationship. Here's where Frege starts. In mathematics, we have functions and arguments. So we have a function on 2 and 3. One such function is addition. So you take 2 and 3, apply this function to it, and you get a result, 5. So the domain of this function is 2 and 3, its range is 5. The value that it generates is 5. Okay, so he knew that's how things worked in mathematics, and he claimed we can use that notion to help us understand the relationship between concepts and objects. So he looked at this analogy between functions and arguments and concepts and objects and said that's where we should start when we're constructing our logic. So here's some Frege language. Functions, he says, are unsaturated. When given arguments, they become saturated. They go from incomplete to complete. So here's a function. If you want, you can use variables in there, but maybe, whoops, that I changed the symbols. I don't want to do that. Maybe you just put in blanks. All right, that's an incomplete mathematical formula. If you put in x and y, it doesn't become complete because you haven't specified what these values are. They're just variables. That's what just leaving a hole communicates to us. If you want a complete thought, then you have to put something in place of x and y. For example, if you put 2 plus 3 in, now you get a complete thought. And what is it? 5. So that's Frege's language. If you're just talking about the function and you don't say what it's a function on, you have an unsaturated thing that you're talking about. Once you fill in what the variables stand for, when you're given the arguments, you then go from incomplete to complete. And he says, look, that's just the way concepts work. A concept, he says, is just a function whose value is a truth value, where the thing that saturates a concept is the analog of an argument for a mathematical function. So that's a weird way to talk, but what are concepts? Well, the concept of being blue, of something that's blue, is a concept. It's incomplete, unsaturated, because we can't get a truth value from this thing alone. If we're going to do so, we have to fill in a value for the space that comes after the concept. What thing are we talking about? If we're talking about my coffee cup, it's not blue. So if you put in my coffee cup, this formula with my coffee cup filling in for x has a value, false. If we take the sky on a cloudless day, let's say, and fill in for x, then the value of this concept filled in, saturated by a cloudless sky is true. So notice the key elements here in Frege's talk about the new logic that we're going to have. What we are going to have are concepts. We can call these predicates, but Frege calls them concepts. So if we've got predicates come in different varieties in terms of their what we now call arity. The arity of a predicate is how many places have to be filled in order to generate a complete thought. So if our predicate is the predicate is blue, the concept of blueness according to Frege, this predicate has an arity of 1 because you get a complete thought by filling in one space following it. Other predicates have an arity that is higher. So if our predicate is sibling, let P be the sibling predicate, the concept of a sibling. In order to get a complete thought, you now have 2 spaces that need to be filled in, because sibling is a 2-place relation. There are also 3-place relations, is between. X is between Y and Z. You can't just stop with 2 things, and you certainly can't stop with 1. You can't get a complete thought by saying Columbia, Missouri is between. That's not a complete thought. You can't say either Columbia, Missouri is between St. Louis. That's also not a complete thought. You got to introduce a third thing. So if you say Columbia is between St. Louis and Kansas City, now you have a complete thought, and it's a thought that has a truth value, in this case, the truth value true. So the thing to notice is we're going to use concepts. We're going to talk about concepts, or as I will typically talk about, predicates. The arity of that predicate or concept, how many places have to be filled in order for us to get a complete, well-formed thought, grammatical sentence, and then an associated truth value. So notice what the semantic devices here are aimed at producing for us. They culminate in a truth value. That's what it is to develop a semantics that is truth theoretic, aimed at truth itself. Once we have that, of course, we're in a position to use sentences understood in this way to characterize arguments that are truth-preserving and those that aren't. Typically, that's called a valid argument in logic, because it's truth-preserving. It's impossible for the premises to be true and the conclusion to be false. So to summarize, here's the way Frege talks. Concepts, like functions, can have one argument, place, or many. If only one, then it's a monadic concept. If 2, a binary one. If 3, tertiary. This is the general concept of the arity of a concept or predicate. Frege's language is that objects fall under concepts. So my coffee cup does not fall under the concept blue, but it does fall under the concept black. Why? Because the sentence my coffee cup is blue is false. The sentence my coffee cup is black is true. So the official way of characterizing this kind of inclusion of objects under certain predicates is, Frege says, objects fall under concepts. Now, Frege also has, besides first-order concepts, higher-level concepts. So, for example, you can say the property of being red is different from the property of being blue. Here, the different from relationship is a second-order concept, and the things that fall under it are first-order concepts, in particular, the concept red and the concept blue, if we use Frege's notion of concept rather than my notion of property. So 2 concepts can be related so that one might say that the first is contained in the second. This is another kind of second-order concept. For example, the concept black is contained in the concept black horse. So the contained in relation is a second-order concept that relates first-order concepts like being black and being a black horse. Here, black doesn't fall under black horse, but is rather, as Frege would say, a mark of it. So, first-order and second-order concepts. A first-order concept is one that takes objects in its argument place. For example, blank is president. You put in, well, as I'm talking about this, you put in Trump, but by the time you hear this, you'll put in Biden, at least unless disaster strikes our country. Second-order concepts are different in kind. The paradigm examples of second-order concepts are, for Frege, number and existence. So, number is not a first-order concept. That should surprise you a little bit. Why isn't it a first-order concept? That has to do with Frege's philosophy of mathematics. But in any case, that's crucial to the understanding of Frege's system, though not to understanding the logic in question. The one about existence is more interesting. This allows, by the way, a way of saying you can't do what the ontological argument tries to do in Anselm's presentation of it, because existence isn't a property. Kant famously complained that existence isn't a predicate. Frege takes his result here to sustain something about what Kant had to say, because when Kant said existence isn't a predicate, it wasn't clear what that meant. I mean, it looked to be obviously false. Take the sentence, God exists. Whether that sentence is true or false, it has two parts, a subject and a predicate. What's the subject? God. What's the predicate? Exists. So when Kant said existence isn't a predicate, that was a truly perplexing claim and looks to be about as obviously false as anything can be. You look to the grammarians for the distinction between subjects and predicates, and then you ask the grammarians, can the word exist or exists function in the predicate position? And the answer is obviously yes. Other things that Frege said were not first-order concepts are things like quantifiers. Here's how you end up with the conclusion that existence is a predicate. So quantifiers, the things in logic that we represent with the upside down A and the backwards E. So for example, everything is blue, something is blue. The top one is a universal universal quantifier, everything. The bottom one is an existential one, something. Frege's understanding of the universal quantifier is that it's a second-level concept. Any instance of one concept is an instance of another. So Frege is here thinking about all SRP judgments. Everything blue is colored, for example. Any instance of the first concept is also an instance of the second. Now notice this claim about quantifiers is not fully general because it doesn't work unless you've got two concepts in there, but it does give us a way of understanding what motivated Frege. Everything blue is colored just says any instance of one concept is an instance of another, and so that's a second-level concept. Particular is also a second level. There are instances of that concept. So if the concept in question is a first-level concept, the claim that there are instances of it has to be one level up. Notice we could then generate a hierarchy of levels of concepts. If you've got existence as a second-level concept and you make some remark about some feature of a second level concept, you'd end up with a third level concept. In any case, we get this hierarchy of levels of concepts so that the quantifiers are treated as second order concepts. So the notion of concept doesn't have to be abandoned if we're going to understand how quantifiers work. Instead, all we need is a hierarchy of concept levels, and the notion of concept turns out to be theoretically fruitful in that way. This, by the way, fits with something else that Frege is doing. He quantifies over expressions for functions and concepts itself. So this is a side item to consider. The logic he's developing is a second order logic. So a first order logic has these two quantifiers in it, and they're followed by variables. They bind variables for objects. So if you think about the two central semantic elements, let's call them objects and concepts to follow Frege. The X here has to take something from the set of objects that you've got, as does the Y. So you can fill in a value for X or for Y by citing something in the other position, which will be a concept, or as I prefer to call them, a property. So you could have something is Y. There exists a Y such that Y is blue. And this one says for all X, X is a thing. Is a thing is a predicate which expresses a concept, and X is a placeholder for an object. That's first order logic. Second order logic allows you to talk about functions themselves or concepts themselves. So sometimes in mathematics you say things like function f has a wider range than function f prime. Or you might say, generalizing on that, every function is superseded by some other function with a wider range than it. In that case, notice you're quantifying over the function itself, but functions and concepts are the same kinds of things. They're analogous to each other. And so if you're going to do that, suppose you've got a simple sentence in our logic. A is F. Let A be a person. Who's your favorite comedian? Let's say A is funny. There's a comedian that I think is sometimes funny. So let A be Ron White. Ron White is funny. You can generalize on the object position by going for all X, X is funny. That's of course false. But what is true is that if Ron White is funny, then something is funny. That's good. If you're gonna introduce quantifiers for the predicate position itself, you'll say for all predicates P, Ron White is P. That's of course obviously false, but that's a way of generalizing on the initial atomic sentence that we started with. And we could then do two different kinds. This is not the same kind of quantifier. I wish I could do one in cursive and one not in cursive, but I'm not capable of drawing that well. That's generalizing on both positions with universal quantifiers, but one of them quantifies over the predicate position and one quantifies over the subject position. If you have quantifiers that allow you to generalize on the predicate position, that logic is called second order logic. If you just have quantifiers that quantify on the object position, generalize on the object position, that's first order. So this is something we're going to come back to later. So think about the following sentence. Blank is a more difficult concept to acquire than blank. For example, the concept horse is a much easier concept to acquire than the concept infinity. We'll come back to this issue later because Frege is going to be forced to say something really strange about examples like this. But at first glance, it looks like a second-order concept. Is a more difficult concept to acquire than is a relation between two things, and it looks like it requires the two things to be concepts. So you've got C and C prime. C is a more difficult concept to acquire than C prime. That looks like something that would fit with what we've been saying to this point, but it turns out Frege is going to say no. We'll come back to that, though, when we look at, I believe, concept and object is where this issue comes up. So the language that Frege is proposing that we start with goes like this. Frege's new logic is best understood in the following way. So first, you develop the syntax of the language, which tells us what the logical form of every sentence formulable in the language is going to look like. So you introduce some symbols, and then you introduce rules for putting those symbols together. So once you culminate the rules culminate in an explanation of what counts as a well-formed formula. As we would say in English, a grammatical sentence. Grammatical sentences then have truth values or express truth values. Frege wants to say they refer to truth values, but in any case, they're linked to truth values in some way or another. So, what does our language look like? Start with the symbols. Frege first introduces names, and then variables for names. Second, we need predicates, or relations. Relations come with a number of different places. That's the arity of them. And so we introduce relations into our language. And if you're going to have a second-order logic, you're also going to need relation variables. Our standard logic, if you've already taken logic, was a first-order logic, not a second-order logic. So we typically don't have these kinds of quantifiers. You introduce a language in terms of symbols. You say how to put the symbols together in a way that gives you a well-formed formula, and then you are done with that part of the syntax for the language, because then the last thing you say is nothing else counts as a well-formed formula except in virtue of satisfying the clauses that we just said. The result of this will be if you're using Frege's approach, both of these formulas are well-formed formulas in second-order language. And a result of this is we get certain metaphysical payoffs. For example, Frege says, existence isn't a predicate. It's not a first-order concept, it's a second-order concept, so the ontological argument is going to fail. He may be right about that, but that's one of the payoffs here. Second thing is, universals don't exist because they are concepts, not objects. This is absolutely crucial. So if you go back to Plato, Plato thinks universals exist. He calls them forms, at least the early Plato, and probably the middle period Plato held this view as well. There are forms, they're abstract entities. So justice, virtue, those sorts of things. Those kinds of terms in language express universals or forms, abstract entities that help generate the truth conditions for certain claims about acts that are just, character traits that are virtues, and the like. Here, Frege's firm divide between objects and concepts undermines such a view. Universals are concepts. The only things that exist are going to be objects. Things are complicated here by the second-order nature of Frege's system, because we have names for relations, and we'll see all of this come to a head when we get to the concept horse paradox. So here's the I guess the end of the story. Maybe this is the clickbait line. Frege says the concept horse is not a concept. It's an object. That's got to be one of the most remarkably dumb things you've ever heard anybody say. Just think about what you'd have to mean. I have no idea how you can bite this bullet. The concept horse is not a concept. It's an object. And remember, it's crucial that the class of concepts and the class of objects don't overlap at all. In any case, what we get is an abandonment of the Aristotelian logic, because we can represent everything going on in the Aristotelian logic in terms of this new logic involving functions, arguments, quantifiers, and standard connectives. And the new logic is much more powerful. Notice, for one thing, it can easily represent particular judgments, whereas the subject-predicate logic of Aristotle could only represent general judgments. Notice what we also get. This is crucial to understanding Frege. We get a sharp distinction between the surface grammar or structure and the real logical structure. This comes to play especially when you look at simple attributions of existence. God exists. Unicorns don't exist. The surface grammatical structure divides that sentence into two parts, as it does with any sentence. It has a subject and it has a predicate. But existence is not a predicate. The proper logical representation of that sentence is if God is a name, there exists an X such that X is God. Notice there is, whoops, that's not right. That's pretty funny. That makes God be a predicate rather than an object. If God is a name, you'd say there is an X such that X is identical to God. And now ask yourself, where is the predicate in here? The only predicate that you might point out is being identical to God. And that's a predicate satisfied by some object in the domain. But the only place the language of existence shows up is in the quantifier. So this will turn out to pay enormous benefits later on, but the important thing is surface grammar and logical structure can come apart. There's also a problem about the difference between natural and ideal languages, but this will come to play. Lots of people, Frege included, thought the best thing we could do for language was to purify it, turn it into a more ideal language in some ways. Exactly how we're supposed to do that or whether we need to isn't quite clear, but the idea here is that the formal language that Frege is introducing is in some ways more ideal than natural language. Sometimes people think we should just be replacing natural language with this ideal language for purposes of math and science. In the last part of the course, we'll look at Quine and Davidson, who say there's something going on here that's significant, but is there any optionality involved in representing the logical structure of a sentence in natural language in one's preferred ideal language? Quine and Davidson are going to say yes, but Russell's going to say no. That turns out to be something that we'll talk about later, but for present purposes, the important thing to notice is the logicism of the Frege proposal. At bottom, he says, all of mathematics can be done within logic. We can reduce mathematical inference and argumentation to the kind of inference and argumentation that involves logic alone. So here's a quote. Nowadays, it seems more and more supporters are being won by the view that arithmetic is a further development of logic, that a more rigorous establishment of arithmetical laws reduces them to purely logical laws and to such laws alone. I too am of this opinion, and I base upon it the requirement that the symbolic language of arithmetic must be expanded into a logical symbolism. I shall now have to indicate how this is done in our present case.